Berlin. Welcome, everybody. My name is Sampath Kannan. I'm the Associate Director here at the Simons. Most of you probably have been to the Simons in the past, but for the few who haven't, a brief introduction to the Simons Institute. It was founded in 2012 through a generous grant from the Simons Foundation, which continues to fund us. It's unique in computer science. It's one institution for bringing together people for sustained collaboration, such as what's happening in this program. It brings together the top researchers in theory, both senior researchers and emerging stars. So it's a great place for launching a career in theoretical computer science for students and postdocs, as you know. But it's not purely only about theory. It also tries to apply the algorithmic lens to look at other disciplines. So we have had programs that bring together computer science and economics, looking at mechanism design and game theory from a theory perspective. We've had lots of programs and continue to have lots of programs in quantum computing because we are a center of that. So we bring together physicists and computer scientists there. We've had programs that bring together neuroscientists, psychologists, animal communication experts, all kinds of things, because theoretical computer science is an imperial field. It looks for other disciplines to conquer, or at least be part of, let's say. And I would say this program is a bit in that vein. I mean, it is not going far afield like the other ones I mentioned, but the idea of really thinking about hardware anew and thinking about what are the right computational models and what we can do in these computational models is an exciting one, and it brings together maybe people from different perspectives, maybe not that different, but ranging all the way from pure theorists working on algorithms to people much closer to the hardware. So it will be an interesting challenge for us to come up with good models to work on for the future theorists to work on. So welcome, everybody, again. Enjoy this workshop, which has been put together by Kirk and other organizers. And one housekeeping rule, as Kirk mentioned, we do not allow food or drink in the auditorium. So enjoy your food and drink outside and leave them outside when you come in. And I will hand off to Kirk now.
Just wanted to introduce the organizers, so maybe you guys can stand and just. I'm Kirk Prush. I'm University of Pittsburgh. I do algorithms.
Organization.
Washington University, Cyprus. I do parallel algorithms.
Shachar Kvatinsky from the Technion.
Pierre Mendu-Garland from the University of Utah.
All right, and I think Sampath introduced the theme of the program. So this is the boot camp. So this is supposed to, boot camp is sort of introduction for people who are haven't been working in this area. So there's sort of, there's three sorts of talks. One, systems talks that are maybe a little backward looking, how did we get where we are? A lot of systems talks that are forward looking, like where does things look like they're going? And then there's some algorithms talks about experienced algorithms. Researchers have worked in this area, and they're going to talk about their research in the area so you get a feel for what it's like. And so let me introduce Shahar, who will introduce our first speaker.
Hi, good morning. So I will present the first speaker, and like the cliche, he needs no introduction, Professor David Patterson, currently in Google, but is actually local, emeritus professor here. Received the Turing Award in 2017, many other awards that will take us the entire day. So let's take Dave.
Okay, thank you. All right, I don't know when you guys last took your last computer architecture class, but a lot has happened, and so I got two parts to this talk. The first part is going to talk about these giant changes that have happened in the field in the last 20 years and why they happen and what it looks like in the future, and then I'll do a question and answer period around that. And I think this is 35 or 40 minutes for this part, and then we'll take a break. And for the last 4 or 5 years, I've been working on the carbon footprint of computing, and we'll talk about that, assuming there's time. And if you get interested and you want to go into more depth, the first book there, which some people call Patterson and Hennessy, I don't call it that, is the sophomore book that kind of introduce you to computer architecture. And then the one that we do for seniors and grad students is sometimes called Hennessy and Patterson. It's the grad student's text, and I'm delighted to report it's not on the screen, but it'll be available next month, the 7th edition, so 35 years after the first edition. We've done it got one more out the door. Okay, what's the underlying technology? It's silicon, right, is semiconductors. So silicon, it starts with a silicon ingot. You grow it. It's about 12 inches or 300 millimeters in diameter, and it's like 60 centimeters or 2 feet long. And they slice it up into little tiny slices. You get these wafers that are 12 inches or 300 millimeters. And then it's kind of like making a pizza. It goes, except 100 steps where they pattern it to get the transistors on there. Then they test the wafer to see if the whole wafer's bad. They throw it away. And then they dice it up into little tiny pieces. It's a big piece of silicon, and because there's going to be flaws in the manufacturing, and we throw the bad ones away, and then we package it, we test it, and there's some parts still fail, and ship it to customers. And so just these two pictures give you a lot of understanding of what semiconductors are about. So these are 2 wafers, 300 millimeter wafers. And this one has dies that are 12 by 11 millimeters, and this one has dies that are about twice as big. So there's about twice as many small ones. So not only you get more for the same wafer, which is basically the cost, because there's flaws on the processing, you're much more likely for a bigger die to have a flaw than a smaller die. So not only you get more dies, you get, after you adjust for flaws, it's even more. So there's a great pressure to try and make dies smaller, or if you make them bigger, your yield's going to go way down. They'll get very expensive. Now, one thing that people do is they will put, like for memory structures, they'll have extra rows in common so that they can swap them in. So that adjusts it some. That's the fundamental idea of what's going on. So the big deal, I said there's going to be 2 sea changes I'm going to talk about. Hey, Mark. This first one is Bob Dennard. He's the guy who invented the DRAM. And he made this observation, I guess, almost 40 years ago. Is like, how can we keep putting more transistors in the chip and the EX will go faster and the power's the same? And he said, because we're reducing some of the key factors as we put more transistors on the chip as they get smaller. And the net effect is that the power dissipation per circuit goes down by about the same amount as the number of circuits go up. And so kind of for decades, it was microprocessors around 5 watts. And so this was amazing. It went faster, put more on it, and the power doesn't change. That sadly ended around 20 years ago. And this was the first sea change. So Intel was building a microprocessor, thought, no, we'll be able to do it one more time. They built it. It was far too much power, so they had to change courses. So what were they going to do? We can't keep building what programmers want, much faster processors, much higher clock rates. You don't have to change your program. Everything runs fast. And so there was nothing left to do. So, OK, we're going to have to go to multiprocessors. So it wasn't like we had the good news is multiprocessors are still binary compatible. The same programs could still run. But there wasn't a breakthrough that made parallel programming easier. It was just this is the only thing they had left. And so we could run programs that could take advantage of lots of processors faster. But if you only use one processor, it probably wasn't going any faster. But that was forced by the ending of Dennard scaling. And so I'm going to capsulize like 30 years of computer architecture in the next slide. But these are about the 11 principles of, you could say, of computer architecture. So I talked about Dennard scaling, and while it worked, it was fantastic, but that one's come to an end. Then, big ideas kind of in computer science, abstraction. Everybody uses that to hide complexity and provide an easy interface. In computer architecture, our guidelines are to make the common case fast, and then 3 ways we make things faster. Basically, parallelism, like with multiple cores or maybe multiple execution units. Performance via pipelining, so like the car assembly line, if you break a manufactured car into 15 pieces, you can have 15 cars going through at once. Microprocessors will have like 15 stages of the instruction pipeline, so we can get them going. The other one is prediction. Rather than wait to know the answer, you guess what the answer is going to be. And as long as you have a mechanism, as long as you're right most of the time and you have a mechanism back out, we can do that as well. So those are the 3 things that drove the designs. And then hierarchy of memories. Principle of locality, hierarchy of memories. Goes all the way back to von Neumann with that concept, and it It's critical today. We're not going to talk so much about dependability via redundancy, but that's another principle. And then I'll talk about the next three things later. So capturing what's happened since you last took a computer architecture class. What are microprocessors doing today? So the first thing we talked about went to multi-core. So how many cores in one of these server chips? So a server chip goes into the data center. It's bigger than what goes in your laptop, but it's what you have in your laptop is similar. So typically 64 to 128 cores in a server, and each of them are two-way multi-threaded. So from a programmer's perspective, to keep it busy, you might need 256 threads to keep it busy. The clock rates are 3 to 4.5 gigahertz. So this is less than a nanosecond, like a third of a nanosecond to a fifth of a nanosecond. And then clock rates aren't fixed anymore. They have what's called turbo mode. Because it takes a while for a chip to heat up, for a while you can run it faster. So a typical clock today, this is running all 100 cores, might be run 10 or 30% faster for a short period burst of time, which is turbo mode in the car, so like tens of seconds to minutes. And then if you have a sequential program, all those cores are idle, well, you could burn a lot more power. And so this single core temporary mode might last for hours. So this stuff is probably good in the data center, and it's fantastic for benchmarks. You can stick your laptop in a refrigerator and put it in the turbo mode and run the programs faster. So you'd think you might be limited by fetch one instruction time, execute it. Well, computer architects went by that a long time ago. They called it superscalar. Modern machines fetch up to 8 instructions per clock cycle. If you are at Intel or AMD, you've got this old-fashioned instruction set with these really complicated instructions. How are you going to pipeline them? Well, the hardware on the fly translates them into what I call RISC instructions, and then we pipeline that. What else do they have to do? Okay. Oh, that's not good. That's not a good thing. Okay. I guess I will. Yeah. Oh, God. Anybody have it? Oh, okay. I'll go out. I'll restart. Maybe that'll do it. Okay. All right. Where were we? And then, if you read the instruction set of like the x86, it might have 16 logical registers, but that's going to limit your performance. You're going to have pipelining conflicts. So a typical modern microprocessor will have 300 physical registers, and like a compiler will rename to explore. The hardware will rename the registers, the 16 in the machine, to these 300 physical registers so they can more likely pipeline. So that's kind of the standard instructions. They also have what's called SIMD instructions, standing for single instruction multiple data, and they operate on 128, say, to 512 bits at a time. So in one clock cycle, they chunk along. And you can break it up into different sized data elements. If it's 64-bit, you could have 8 to 64 things calculated all in one clock cycle. Or if it's small, 8 bits, you could have 16 to 64 of them all in one clock cycle. And then the memory hierarchy. So modern microprocessor for a server has 3 levels. It'll have, at the instruction cache level, very fast, like 32 to 64K bytes, both for instructions and data, so they can do it parallel. And that's for every core. And then every core also has, okay, I am going to give up on this thing. All right, I know what to do. I guess I'm here to debug the technology. That's another role that the hardware people play. Systems people will debug. Okay. Then you've got a second level cache. Every core's got a second level cache of 1 or 2 megabytes. And besides that, the whole chip has a third level cache of 50 to 100 megabytes to back up everything on the chip. And then I talked to you about speculation. They have a very sophisticated branch prediction, which is critical to get all this out of order. These instructions are executing, in fact, 8 at a time, executing out of order. It appears to the programmer they're in order, but the hardware has to keep all that going. And so typically what will happen is each core will have hundreds of instructions in flight per core, and maybe hundreds of memory accesses in flight. And then why is that limited? It's limited by these physical things, like the reorder buffer allows you to execute out of order, how many physical registers you have, reservation stations on every unit kind of buffers, and how long your load and storage use. And if you do all that, people say, okay, pretty good job if you get that all working. So this is far from the PRAM model, right? But that's what's going on today inside of one microprocessor. Okay, so Gordon Moore, Berkeley alumnus, 60 years ago made the most amazing prediction, in my view, in the history of computing. He plotted how many transistors per chip over a few years. I think maybe as a joke originally. He said, I think it's just going to keep going. And in the paper that he did this, which is an amazing paper, this was 1965, he said, what does this mean if it's going to keep going? Well, in the future, stores will have, along with cosmetics and buttons, there'll be home computers. He said, this will happen in our lifetimes. And a dozen years later, Apple fulfilled his pledge by making a commercially shippable microprocessor, a personal computer. Okay, now, what's the memory, besides the processing, the logic, there's the memory underneath it. There's two types. Static RAM, that's very fast. It's 6 transistors per cell. It's to keep it that speed. And then the very dense one, which is off-chip memory, called dynamic RAM or DRAM. This is what Bob Dennard invented. So it's a lot faster and less energy to be on-chip for SRAM. But if you want to have a lot of SRAM, the die gets really big, and that goes back to, it gets more expensive because it's fewer per wafer. And the other kind of, as Moore's law and things are starting to slow down, the SRAM isn't actually getting any better. The SRAM cell, even in a smaller technology, where logically the transistors should be smaller, the SRAM cell is still about the same size, so that's not a good thing. It's a lot more expensive. It has high bandwidth, but capacity is more expensive because of the die size. DRAM, the bandwidth is expensive because it's off chip, but it has a lot more capacity. Okay, so what's going on? So SRAM has plateaued. The DRAM is growing. It used to be like clockwork. Every 3 years, you got a factor of 4 more DRAM. For decades, this was true. Recently, that slowed down to the factor of 4, probably about 10 years apart. There's all kinds of interesting, because of the kind of the slowdown of DRAM, people are exploring alternatives, and the various names, phase change, magnetic RAM, resistive RAM. But it looks today like none of those are going to make it. Over my long career, there's been 2. It used to be core memories, magnetic cores, and then it was semiconductor. And then flash memory actually made it, but it's rare that a memory technology comes along. You'll hear lots of speculations about it, but it's difficult to be commercially viable. So flash has actually got a very rosy future. Flash memory, they build 3D structures, and the people I know in the flash industry don't see any walls coming, but SRAM and DRAM are facing this. And then the slowing down of Moore's law. Now, for my colleagues in electrical engineering, I think, over their careers, they say, family and friends say, what do you do? Is I make Moore's law happen. And so when I say that Moore's law is slowing down, that's like fighting words to them. That's like an insult. So literally, they will agree that Moore's prediction of doubling every year or 2 years, which was primarily by making the transistor smaller and making the chip bigger, that's over. But what they're talking about is maybe we can use packaging or something like that to get the effect of Moore's law. But yeah, this is fighting words when I say that, but I think people would agree that this era is over. Now, Gordon Moore, an exponential can't live forever, and he said about 20 years ago, we've got another 10 or 20 years, but I think we're past that phase. And the other thing that's happening economically is there's kind of, and semiconductors has 2 pieces. It's the memory piece, which is a different technology for DRAM and flash than processors with logic. And there used to be lots of companies doing the logic. And then maybe 10 years ago, there were 3. It was Intel, Samsung, and this company, Taiwan Semiconductor Manufacturing Company, which had this novel business model, is we're not going to design our own chips. We'll make chips that you design. And what's happened today, if you read the newspapers, Intel's in big trouble, Samsung's falling behind. So the leading company in the world that makes logic semiconductors is TSMC in Taiwan. And they'll make them for anybody. So it's extraordinarily valuable. NVIDIA, which we read about in the paper all the time, does all the chips there. What do you, Mark?
As a hardcore double E,
Yeah.
I will say that Moore's law is definitely ending. The numbers we have in these technology nodes are marketing numbers.
Yeah.
They're not even feature size
Yeah,
anymore. So you're right.
Thanks. I knew Mark would. Mark's at least half a computer scientist. So, yeah. So what happened is there was a technology change. These numbers used to mean something. You could measure distances and it mean something. And then there was a technology change that Berkeley helped pioneer called FinFETs. And it was better, but the lines weren't that much smaller. So they said, well, this is as if it was this small. And once they went away from measuring something to as if it was this small, then these numbers here are actually called Intel 10, Intel 7, Intel 5, and now it's just straight marketing. So, but I think it's another indication of towards the ends of Moore's law that these things are happening, where they used to measure stuff and now they're kind of pretending that it's really good. So when did it end? Well, according to the New York Times, that's my source. It's ended May 18th, 2016. How did they pick that date? Well, what the New York Times said, this is Moore's law, and they said doubling every 18 months. It says when Google starts building their own chips, it's over. So that introduces the next sea change. So the first sea change was end of Dennard Scaling in, so we have to go to multi-core from one core at a time. Programmers would much prefer we had 50 gigahertz chips with a single core, but we can't make that. So those chips I was talking about, 128 cores, out of order, actually all that stuff, people, that's not good enough. But we don't have another idea that keeps it better and is more slowing down. So, and then all the investment in the history of our field has all been general purpose microprocessors. You make those better, it lifts all boats. There's nothing left. Whoops. This one exception was the GPUs. GPUs actually go back 25 years, and for that the games market, they had their own niche. That was by far the best one. You didn't use CPUs, but that was that one niche. Everything else was general purpose processing. And maybe you get 10% gains per year now, and maybe they're playing games with the turbo mode, but maybe 10%. If you're happy with that, then things are rosy. But programmers got used to when things would double every 18 months or 60% per year. So what are we going to do? There's only one option left that domain architects know about, is that we'll make it specific for a narrow domain. So what that means is we can make that one domain go really fast, but you're not going to be able to run all the programs in the world. That's always been an option, and now we were forced into it. And you want to do more than just the graphics market. And John and I, when we got the Turing Award, our Turing address was a new golden age for computer architecture. What did that mean? We meant because we're going to have to design architectures for these domains, you're going to need more architects. There's going to be lots of opportunities for research here. And coincidentally, just about the same time is standard architecture hit the wall, AI started to blossom, right? The deep neural networking branch of machine learning branch of AI started working about a dozen years ago, and that's about the same time as this transition. So how has this changed? That title is supposed to be wrong. Oh, I screwed it up. Okay, let's do it this way. All right, so in the CPU world, these are incredibly important. Binary compatibility. We ship programs in binary, so that's hugely important. Breaking the binary compatibility, it's like boiling an ocean. There's millions of programs out there. You can't change the binary. The source code is millions of lines of code, amazingly enough, in C or C++, and millions of people writing these programs that compile them to that native one. And can you change the software to match the hardware? No, they're not going to do that for you. Software is king. Hardware people have to fit the binaries, and you have to figure out how to use it. They're not going to change the software for you. So what's happened about DSAs for artificial intelligence? They don't care about binary compatibility. That's irrelevant. How big is the code? It's only hundreds of lines of PyTorch or JAX is what these models are. And then there's this lower level library routine. How many people are writing that? Well, at Google, it's probably tens of people writing what's called the Palace code underneath JAX. And NVIDIA's got more people. Maybe they have hundreds of people. But when a new architecture comes out, they rewrite the libraries. But it's a small number of people who do that. And so unlike in the CPU world, the machine learning people will adapt. If you have a good software stack, they will modify it to run well on your hardware. So it's this is a very different universe than we're used to. And this is a reason why, despite the ending of Moore's law, we see gigantic gains in running this domain-specific architecture.
Do you think that's a feature, or it's going to grow as we get more and more AI? Will the tens to hundreds become?
Yeah, I'll talk about that. I mean, you're going to have to make your own predictions about how important AI is today and how important it will be in the future. But if you believe it's important, this is where the investment is being made, and as I'll mention again. So I didn't know Mark was going to be here, Mark Horowitz. But in my view, plausibly the best keynote of all time. A dozen years ago, Mark gave a keynote address at the main Semiconductor conference, and he pointed out that energy limits to what we can do. We kind of have this crazy model. We'll take a RISC instruction, and the whole thing is about 70 picojoules of energy to run it. This is hitting the cache, this is reading the registers, there's some control, and the amount that you do in addition is it's 1%. So this is a crazy thing to do if you're going to do a lot of arithmetic. And it turns out, for machine learning deep neural networks, it was like God asked a computer architect, okay, there's one thing you can accelerate, and it's multiple choice. What do you want? And they'd say, matrix multiply. We know how to make matrix multiply go fast. And that's what they want, is matrix multiply. So we updated Mark's slide to talk about the relative. So we want to do SIMD instructions, right? Not one at a time, but lots of things. We want to do actually a whole matrix multiply. And then we want it to be narrow data, and I think this will work. So for more recent technology than Mark did, there's about a factor of 30 to 50 between 8-bit adds and multiplies. So it takes 50 times as much energy to do 32-bit as it does to do 8-bit. And then if we compare that to the on-chip SRAM, those are 300 to 2,000 times. You can do, in the same amount of energy of SRAM, you can do 2,000 8-bit multiplies or 300. And if we go off-chip to DRAM, then it's many thousand. So given you're limited by energy, what do you want to do? You want to have instructions that especially do matrix multiply in narrow data. So Jim Demmel's here. He and I, early in our careers, spent a lot of time on the IEEE floating point standard, which was 64-bit and 32-bit, and that's like what God intended. Velvel Khan was the God. And he said, that's all you need, and precision's the most important thing. This is a new world. They not only have, Google helped pioneer a 16-bit mode, which is plenty, and now 8-bit, and there's even 4-bit. 4-bit floating point is a thing. There's only 16 values, and they call it floating point. And then there's 8 and 4-bit integers. So because of these things on this slide, there's huge push to make it smaller, and not only do you get the benefits of less energy for execution, it also takes less memory capacity on chip, which is precious for AI, and then less memory bandwidth. So kind of remarkably, I did not expect in my lifetime, after the IEEE floating point standard, that I would ever look at floating point arithmetic again. And now it is being driven by this application. It's this, why is this happening? Because of the value of AI, this is going on. And so if you're doing scientific computing, there's going to be huge performance available if you can get your work done with narrower data. But Khan taught us that you need 64-bit. Jim? 2 bits. Yeah, no, it's there's people talking about training with a single bit and ternary and stuff. It's not clear what's practical there, but absolutely 8-bit is practical today, and maybe smaller. All right, so this is an example. The way Google does it, they do these big matrix multiply units, and you can see over time as the technology improved, they got more of them. We happen to use systolic arrays, which came from the theory community long ago. That was done in the past because trying to reduce the area from matrix multiply units. We're doing it today because it's much more energy efficient. But you can, with newer technologies, we're putting more logic in. I don't know how close you're going to get to the hardware, but this Roofline model might be useful. It was actually developed by my PhD student, Sam Williams, who works up the hill at Lawrence Larkin Lab. So it's got inspired because I inspired Sam because I thought the text is too long. I can't read it. So he came up with a model. So what's the model? So on the y-axis, on the log scale, is peak performance. That's what high-performance computing people in AI chips talk about. So if the log scale is peak performance, then you'd think there'd be a flat line in the peak performance. And then what the x-axis is what's called the operational intensity, which is the number of operations per byte. So if you do 50 floating point operations per byte, it would be 50. So it turns out, since this is operations per byte, this sloped line is the memory bandwidth of it. And so what the purpose of this model is to point out, just because it has high peak performance doesn't mean your program's going to be able to take advantage of it. It's going to depend on your operational intensity. And then part of the Roofline model name was, what's this point, which we call the ridge point? That's when it's perfectly balanced. It's exactly memory bound and compute bound. So you can see if the ridge point's further to the left, a lot more programs will be able to operate at the peak performance. And so 2 specific examples. Right now in machine learning, transformer is the model that everybody cares about. And in the inference phase, there's a pre-fill phase, which is computationally intensive, and a decode phase, which is memory intensive. And you can see then the performance, the maximum performance you can get will depend, for this phase, will depend more on your memory bandwidth than it does there. And so just to put that in perspective, this is what Google's done about 9 generations of TPUs, and this just shows there. And you can see, the very first one we did, we didn't really know what we were doing, and it was memory starved. And so it went over here, and the ridge point's moving over to the right. So far, still like the transformer model, everybody can run the pre-fill well, but the decode is memory bound. Okay, so that's that. So what are we doing with the ending of Moore's law? One idea that people are excited about is chiplets. And as it sounds, a chiplet is a small chip. And so AMD was one of the people who pioneered this. So this particular, what they do is use small chips and use packaging to assemble it into a big chip. So they have a big kind of I/O chip in the middle, and each of these 8 small ones, each can do 8 cores. So they put that together in a package, and they get 64 cores out of it. And you can imagine that's the same chips you could repackage in a smaller package and have 32 cores. So there's a bunch of advantages to the chiplet model. And the question is, what's the cost of the packaging and how much is spent there? If you look at AMD's roadmap, they're planning on getting up. I told you it was at 128 cores today, and they plan to get 256. So they can add a bunch of cores, but the memory channels use up a lot of I/O wires, and that's harder for them to add. And so it'll be, the standard server will get much more computation, but probably be more memory starved going forward. And with this idea of domain-specific architecture, there's also domain-specific memories. The one that everybody uses today is called high bandwidth memory. And what's this idea there is, rather than having DRAMs in these standard DIMM modules that you could plug into your laptop, this is part of a packaging. There's a silicon interposer, and they have a stack of DRAMs right next to it, and there's a limited number. In this case, there's 4 stacks around it. And they actually have to mill the wafer to get it thin enough so they can get 8 of them there. So these are pretty hard to make. Samsung pioneered it, and they're having a hard time making it, and SK Hynix can still make it. So this particular memory technology is almost as valuable as the GPUs that people use to compute on it. And it gets high bandwidth memory by having 1,000 wires. So 1,000 wires connects this over the silicon interposer, and that's how they get the high bandwidth. So the good news about high bandwidth memory is it's incredibly high bandwidth. And you could see from the Roofline model that could limit your performance. The bad news is that you can't put that many chips with it, so it's a memory capacity limit. A very recent idea that just came out down a couple of months ago was called high bandwidth flash. So inspired by the high bandwidth memory stack, where these are standard DRAM cells, they use flash memory to do that. And so what is that? This is this is a domain specific. What restrictions are? Well, it's huge capacity because flash is a lot denser than DRAM. And it's got the same bandwidth for reads, but it's really slow on writes, and it has bigger block size and things like that. So here's an example of another novel memory technology. It's based on a standard technology, so it's not a question to make it, but whether or not there's applications that can use it. Plausibly, if you know machine learning, the parameters or weight memories don't change during serving. It might be useful for that. And then just for perspective, this is all of the TPUs that Google has done, and kind of make sure. So like training is like sending your kid to college, right? And then inference or serving is like your kid graduates and gets a job, does something useful. So Google has built things primarily for inference in that column, and this one is training. It can do inference as well, but it's training chips over time is a factor of 100. Now, they went from 16-bit to 8-bit, but still a factor of 100 per node. And Google early on realized for training, we're going to need a lot of chips, so it built supercomputers. So the first one had 256 chips. The current one has almost 10,000. So it's a factor of 100 improvement in peak performance and a factor of 36 in number of chips in the system, so it's 3,600 over less than 10 years. Now notice that the memory bandwidth only went up a factor of 10 to be able to do that. But this is going on. So I think the next slide is my conclusion, and I'll do the question and answer period. So power limits what we can put in a chip because of the end of the Dennard scaling. No more Moore's law. So we get, the nodes are getting more expensive, and some of the technologies aren't going so well, but that's led to this other sea change. I mean, when I talk about sea change, like in the, 70 years of computing, I don't know what the other sea changes were. We had microprocessors, maybe microprocessor was a sea change. Here's a couple others. Chiplets may become more popular. Memory is a practical limit, especially as SRAM and DRAM don't gain that much. High bandwidth memory is, the coin of the realm. Maybe flash will do this. And this question about how important is AI, as I was in a phone call with somebody yesterday, the investment that's going on right now is the largest investment in capital in humanity's history, right? Companies are spending tens of billions of dollars from the, putting this in perspective, if you hadn't heard about it, Meta/Facebook was investing, I don't know, $30 or $40 billion in hardware, but their model wasn't that good. So it made sense to start hiring people. And I thought it was $100 million, but I was wrong. They're offering $1 billion if you sign a contract for 8 years. And that's, unless you're special, then it's $1 billion for 5 years. And that's been the recruiting pitch. So kind of like, we're musicians and there's a few Taylor Swifts, People with PhDs in computer science and AI are worth $1 billion in the current marketplace. Okay, with that I will pause before I talk about carbon footprint stuff. Yes?
This might be maybe an ignorant question. You just talked about the stacks of chips.
About
the chip stacks.
Yeah.
So is there connectivity going vertically
Yes.
here as well? Yeah.
Sorry, I should have said that. It's called through vias. So the HBM has, it's a 3D stack, and there's wires that are going through, and that's a way they're getting tremendous bandwidth. So those wires are going through, and then they're going to these 1,000 wires that are going out, and that's how they're doing. And so 3D will be one of the directions that people go as a packaging thing. Jim?
Any comments on how interconnects between different computers is evolving since these big data centers
Sure.
are spread out quite widely?
Yes, Mark should speak up too. Google switched over to, so kind of, there's always been this tension between electrical connectivity and optical, right? Optical doesn't have distance, it's much more energy efficient. And people kind of say, well, electrical can't keep going, right? That's kind of this tension. And so kind of often within a rack, it's electrical, and between racks, it makes sense to be optical. There's greater distances. So Google announced a few years ago that they connect between racks using optical switching. So it's actually not packet switching like we do. It's circuit switching. So you can set up a circuit between these two things, and goes down the light thing and go. The question going forward is whether that's going to keep, that split's going to keep happening. It's going to be with electrical from the rack, or, which, we have a colleague who started a company, he thinks we'll put optical all the way in the chip. And so rather than optical just between racks, it'll be optical between chips, optical between chips and DRAM. So some people think that's inevitable, some people don't think it'll happen. What do you think, Mark?
Well, so the interesting thing to me is people are moving to co-packaged optics or copper. So what's
They have a
happening-
choice?
Well, what it's interesting is that the highest speed electrical interfaces right now are what are called co-packaged copper. So you have your package that your die is in, and then you have these little twin-X cables that go down to the package, fly to the connector, and then on the other side of the connector, there's a little cable. This is an electrical cable going to the other thing. And for distances on the order of, a foot-ish thing, 6 inches to a foot, you can do that at 200 gig, and the next standard is pushing at 400. So as long as you can do that for those kinds of distances, my guess is it's going to stay electrical, because the big problem with optics that people don't talk about is the lasers. And there's an enormous amount of power in the lasers that are usually not talked about when people talk about the optical power. And lasers are not reliable. They burn out. So you can't actually integrate the lasers into the thing, because that would, that's not good. So I think in that domain, it's still not clear that you're going to go to optics, but everybody is going to co-package optics when you have to do the thing outside of your rack, or maybe even from top to bottom of the rack. And the integrated photonic stuff that Dave was talking about is definitely going to arrive to do that. And so I think we have another generation of electrical interconnection in.
But there's this struggle, race between the electrical people, and they do digital signal processing, and oh yeah, you can't do it. We did it again, and that's happened many times. And people believe ultimately it has to all be optical. But it's a.
The big thing in the optics thing is you need to build up an infrastructure to test chips that have optical interconnection, and building that infrastructure is, billion-ish dollars, and there hasn't been a big enough market yet to warrant that. I think the AI thing has solved that problem. When Team Green,
the dollar thing is.
Yeah, when Team Green has said that that's what they're doing, lots of people are going to jump and build all the infrastructure.
Assuming AI is making money, right? Assuming, right?
For NVIDIA it is.
Yeah. Yes, go ahead.
So this is a question from 64,000 feet high. Have we, in going from all these architectural innovations, have they allowed us to effectively continue Moore's law, or are we not doing that level of speed up?
This is where, I can make enemies in my department. So some of the things that are happening, what's the signs of the ends of Moore's law? Well, fewer companies can make it, and guess what? If you're a monopoly, you get to pick the price, right? There's no competition. So the cost of wafers is going way up. And so some people have said, it's Moore's law is not the number of transistors per chip, it's how cheap transistors are. That was what they said for a while. But if there's only one company making them and the wafers are really expensive, it's not clear that the transistors are getting cheaper. So it's still the world's best technology for building chips. It's just before this amazing rate of change and things got cheaper and faster, it was just phenomenal for decades. That's probably over. But like I said, these are kind of fighting words.
It's definitely over.
It's definitely over. But you saw what Google did. Google, what are these companies like NVIDIA, Google, they're doing what's called full reticle chips. When you do this patterning, there's this thing that steps and repeats. The maximum size it's 800 millimeters squared. It can't be any bigger than that. So people are just building the biggest chips they can, and because people and charging whatever they want, and people are paying. We're paying. I think for the NVIDIA nodes, they're talking. Is it $30,000, $40,000 numbers? Phenomenal numbers, and they burn thousands of watts. It's the most expensive computing nodes ever, but it has value, so we're doing it that way.
So we know optics has the maximum possible bandwidth, speed of light, but what about the latency of those interconnects?
Well, I assume it's the electrical optical interface is part of the latency. But yeah, no, over distance, it's really good for distance, right? The latency isn't big. Once you've switched, you can go a long ways.
Right.
Its speed of light is a latency.
Well, no, but there's also getting to the network, and it's the interface.
Well, that's a long-held challenge of the
So that's
hardware,
not
software.
so much.
So the way to think about it is behind every optical link is an electrical link.
Mm-hmm.
So an optical link, you have an electrical link, and that has to drive the modulator and receive the receiver on the photo, and then you put the optics in there. So if you took the optics out, the latency would always decrease a little bit, but the added latency added by those optical components is trivial compared to everything else, so that's not really a big issue.
No, let me do one more question, then I'll do the carbon stuff.
So you didn't talk too much about chiplets, but I always thought it was expensive to get a signal off a chip. So it seems hard to see what is an application where you want to make a lot of small chips.
I'm glad Mark's here, but there are standards about chiplet interconnects, and you can see with the HBM, it was possible to get really high bandwidth between them. So I think that's the question. I think what's the cost and latency of the chiplet interconnects versus the benefits you get of putting a lot of chiplets together. But people are successfully making commercial products based on them. But right now, the AI things it's kind of brute force. We can make so much money, we're just going to build the biggest things possible. I think the current NVIDIA one has 2 giant chips, and they put it together in one package.
So the way to think about it is, obviously, the bandwidth you get is the rate at which you run each pin and how many pins you have. And the big advantage in the chiplets is you do a different kind of connection between the chip and the substrate. The substrate is not kind of a normal package. It's actually another micro fabricated thing that has much higher density of interconnects. And so the way we're getting very high bandwidth is to have many more pins, and those pins are running modest rates being 10 gig, 20 gig, not 200 gig. So the 200 gig is very expensive. And that's kind of the trade-off that people are doing. And so when you went into this chiplet with this interposer technology, it basically dramatically increased the number of wires you have between the chips.
Yeah.
Does that make sense?
So let me go in, and I don't know that. I think it's plausible, given if those of us who believe in global climate change, we as an industry have a big carbon footprint, and so I want to bring this up. And there's a bunch of papers that I've been involved in that you can read about, but let me just go ahead. Now, over my career, I have given a series of bad talks. It was John Oster and I, for fun, when we were young, how can we teach grad students how to give a good talk? Oh, let's teach them how to give a bad talk. So that was the first one. And then I later did how to have a bad career, and that's a pretty popular set of slides. And I did how to have a bad research center. So this is my fourth one, which is how to give AI a bad carbon footprint. So what you do is you give bad advice, and then if you don't want to do it badly, I give good advice. So the bad advice is pick the biggest model. You read about scaling laws say the bigger the better, so pick the biggest one. The older GPUs are both cheaper and use less power, so pick an older one. And just use the nearest data center so you don't have to ship the data over the internet. And so if you do that, so we came up with what we call the 4 M's. And these are 4 factors that you multiply together that figures out what's your carbon emissions. The first one is the model itself. So I picked Meta's Llama model, this open source model. It's about 4 septillion floating point operations to train. We picked the first GPU that was actually had optimizations for machine learning. And this is a figure of merit of microwatts per, it's about a teraflop of, so for a fixed amount of floating point performance, how many microwatt hours is it to be able to do that? To make it an M, this is really about the data center, so it's kind of mechanized it. So in the data center industry, there's a figure of merit that they call power usage effectiveness. So if you think of, if 100 or whatever, a megawatt goes to the computing equipment, if you need another megawatt to cool it and distribute power, then that would have a power usage effectiveness of 2. Or if it was half a megawatt, it'd be 1.5. And then the biggest surprise to me is it matters where the data center is. So if you're in West Virginia, where there's lots of coal mines, they use coal power, which is the dirtiest energy source. So if you do it badly, you end up with this figure of 240,000 metric tons of carbon emissions. So let's not do it. Let's not do that. So instead of the biggest model, pick the most efficient model. Instead of the older GPU, use the latest one. Don't use a local data center like on-campus data centers, which have this bad power usage effectiveness. Use one of these efficient ones. And by the way, once you're in the cloud, you can pick the location. So pick a location with low energy. So if we do all that, we can reduce the number of floating point operations trains by almost a factor of 20. The latest Google TPU is like 4 times more efficient than the old Volta. Cloud data centers are remarkable. They only waste 10%, not waste, they spend 10% on power distribution and cooling. So that's almost a factor of 2 better. And then if we don't use coal, if we use hydroelectric power, there's another factor of 10. So you multiply those all together, and it's 1,500 times. If you do it badly, you can do 1,500 times better by being careful on those 4 M's. So in our textbooks, we hit upon this idea of having fallacies and pitfalls. So we explained it, and then at the end, we'd show you, you might think this, but this is not true, so I thought I'd carry this over here. So I think I got started in this about 5 years ago. There was a cover of IEEE Spectrum, the flagship of IEEE, that said, AI is going to burn up the planet. They predicted last year it cost $100 billion to train your model, and as much carbon emissions as New York City per month. So I asked my machine learning friends, is this true? And they said they didn't think so, but they didn't have any data. So that got me on this path. But kind of the guiding principle here for this is energy is physics. We all understand. But when you do emissions, it's accounting, because you're trying to figure out who's to blame for it and what's within your sphere and what's other people's sphere. So that's been part of my education. So the first fallacy is carbon offsets will make the emissions of AI negligible. The companies are claiming we've offset carbon offset. We don't have any carbon footprint at all. So to explain this, I'm going to have to tell you give you an analogy, and then I'll turn it into carbon emissions. So the analogy is you and your friend Max are single, you're young, you're single, you eat all your meals out. And so in a year, that's like 1,100 meals. So people are worried about you and Max, so they start an effort to encourage people to eat organically. And so this organization does this, and if you eat an organic meal, they give you a certificate that says it's organic, it was prepared organically, and you can collect them. And then they make a leaderboard to see who has the most organic meals. So you get into it. Your friend Max just keeps eating whatever he wants. And you get 800 certificates, and you turn in, and you win. And so your family praises you. You get dates. You become a celebrity because you're eating organically. Your friend Max had maybe 100. He just keeps eating those. You think this is great? Next year you go for it, you're going to have to go more. You get 1,000 meals. Almost 90% of your meals are organic. Max just keeps eating the way it was, and you can't wait for the leaderboard to show up, and you don't win, and you're very disappointed, but shockingly, Max wins. How is that? So you confront Max and you say, I've watched you eat. You never eat organically. How could you possibly win? Well, I read the rules, and the rules don't say you have to eat the organic meal. You just have to buy the organic meal. So I found out in San Diego, breakfasts a certain time of year, you can get them really cheap. So I bought 1,100 breakfasts, and I turned them in, and I won. And you say, but look, that's not the spirit. You want to encourage local restaurants to offer organic food, and you want them to offer them all day long. And what you did didn't move the needle because they were serving organic anyways. He says, nevertheless, I'm a celebrity. I get dates. I won. All right. So how does this apply to what we're talking about? So because I told you emissions are accounting, there's what's called the greenhouse gas protocol guidance, where all these companies got together and set up the rules. So one of the questions is, when you say you have clean energy, how do you know that? They set up energy attribute certificates, EACs. So like when I eat the organic food, I got a receipt back for doing it. Similarly, if you use carbon-free energy, for every megawatt, you get a certificate to prove you got it. And those are called bundled EACs. So as you use it, you get it back. But there was this other category, because they're trying to encourage industry to spend money on clean energy. And this other category is called unbundled certificates. What are the rules on this? Well, there's almost no rules. Anywhere in the same continent, you can buy it any time of year. So like Max, they can just buy certificates and claim they're carbon-free. Well, how popular are these energy certificates? So there's an article last year in, I think, The Guardian, and it said Amazon. So this is what's called location-based. So ignoring the clean energy purchases, this is how much you use. So these 4 big hyperscalers produced, everything they did was 38 million tons of carbon emissions. If you believe what they say, Facebook and Microsoft all went to 0. But how did they do that? Well, Facebook actually is pretty close to 0, but Amazon and Microsoft use these kind of misleading unbundled energy certificates to get their numbers. If we ignored that, this is what the numbers would be, much higher. So despite marketing claims that it's heading to 0, in reality, we're still a long way away. Okay, so remember this number, 18.5 million tons of emissions in 2023. But yeah, so we're not going to 0. Another concern is that the data centers are a major consumer of electricity. So an organization called the International Energy Agency that hit some 50 countries, it's been around for 50 years, said in 2022, global energy use by data centers was 1.2% of energy use. And they think it'll probably be 1.5% this year. But even if AI grows or data centers grow, there'll be 4 things that'll be bigger. Just continued economic growth will be bigger. Maybe not surprisingly, electric cars will be much bigger. Air conditioners will be much bigger. And high energy manufacturing like aluminum. So it's not going to be a major use of energy worldwide. But in certain regions, it can be a big deal. In fact, this is from the New York Times, but I think it's the European Union, the US, and China have a huge number of data centers. So in those locations, it might be a local problem, but it's not a global problem. And right now, it's in the New York Times, only 16% of countries in the world actually have data centers. You can see very few in South America and Africa. So it's probably not a global problem, but it can be a local problem. All right. Well, that suggests that maybe the data centers aren't that thing. What about, then the question I get, what about on the edge? So we looked at mobile phones, and basically AI is a very small piece of phones. What the big surprise for the data centers was that, for phones was, it was the chargers that were the big problem. But the display and the radio use most of the energy, but people usually ignore the chargers. But the wireless chargers are much less efficient than wired chargers, and people usually leave them in all the time, plugged in all the time. So I don't know that this video is going to work. But we animated it, but I don't think this is going to work. Okay. All right. Well, you'll just have to trust me on this. But basically, we start off, and it's 0.3 million tons for AI for the energy, and it gets up to about, when you put in the wired chargers and you leave them in what's called vampire mode, it gets up to around 30. But then when you factor in the manufacturing of the phone, it gets up to about 100 million tons. So AI, the operational AI is not a big piece. Okay, here we go again. But okay, so the last fallacy, isn't AI the biggest problem we're facing based on the newspapers? So the numbers I gave you help explain that. So in 2023, we manufactured 1.3 billion smartphones, and that's about 68 million tons of carbon emissions. And for phones, since they have short lifetimes, they don't use that much power, less than 15% of the carbon footprint is operational. 85% is the manufacturing and transportation of the phones. So you remember from before, location-based, where we don't count the energy purchases, for the 4 biggest data, hyperscalers in the United States, that was less than half of that. And for servers, because they have longer life and they use a lot more power, operational is almost all of the energy use. So after we get rid of the legitimate, we account for the legitimate clean energy sources, it almost cuts in half again, so it's about a quarter. But AI is not most of what's going on in the data center. We measured it at Google over those 3 years, and it was between 10 and 15%. So even if let's assume it grew to 25% in 23. So, you got all these data centers. It takes a while to turn all that equipment over. Let's say it was that, so that means in 2023, the embodied emissions of the smartphones was like 15 times the AI operational CO2. So maybe today, maybe we don't make as many smartphones, and maybe AI is a bigger piece, but it's still that the embodied smartphones is a factor of 10 bigger than AI. So I think wrap this up in time for questions. So how can we reduce the carbon footprint? Optimize those 4 M's, the model, the machine, mechanization, and the location. Companies should aim at procuring carbon-free energy that locally that matches their hourly use. There's not just, computer designers are used for designing for performance for total cost of ownership, but we need to factor in performance per data center power. We can't build as many data centers as we'd like. And performance for CO2, those should be equally important. And then we need to if we're going to work on carbon emissions, we need to get the numbers right going ahead. Often the estimates for AI are off by orders of magnitude. After I wrote one of these papers, why have I been working on this? And it's because the claims were off by orders of magnitude. So what I'm interested in now is trying to work on the carbon footprint of making all those smartphones. Okay, with that, open for questions. Yeah, a few minutes. Yeah.
Do you think with all these 1,000-watt processors, we should change the units to horsepower for?
to horsepower? I hadn't thought. That seems like a great idea. Yes.
When you were showing the factor of, I think it was 2,000 with the 4 factor in AI, right? When you
Yeah.
Those 4 things. So if you were at the other end of that, then it would be
Yes.
the problem. And so you're saying everything is at the more efficient end, or?
Well, there's huge incentives for companies to be more efficient. I mean, setting aside the carbon, it's generally, what costs more is when they buy clean energy. That's extra cost, but reducing the energy cost saves them money. Making data centers more efficient saves them money. So many things are aligned with saving money, except for the purchase of clean energy, which is an extra cost. And then the question is, the companies all play lip service to that idea of get the smaller carbon footprint. I would say Facebook or Meta and Google have actually so far, made the investment to reduce the carbon footprint. But that would be the thing to watch for these companies are doing. Because, the huge investments are going into these tens of billions of dollars. So making them as efficient as possible has real dollars and cents savings. And if you reduce energy, that probably saves money. The one, at least from a Google perspective, from NVIDIA's perspective that is selling chips, it's less clear whether or not they had that same motivation, except for trying to be a good corporate citizen. Yeah.
So one of the compute-heavy kernels is GEM, matrix multiplication for AI. And then, as far as I know, all hardware accelerators are based on the classical cubic time algorithm and not on the Strassen-like fast matrix multiplication algorithm. Do you have?
That we've talked about that a lot. I think the question whether Strassen, besides being theoretically more efficient, in hardware is actually more efficient. Is that, Mark?
I believe it only is more efficient at numbers of bits that are much larger than what people are doing. So certainly for small number of bits, like 8, it's not more efficient.
But for much bigger precision, it could be. Yeah. Well, but if somebody comes along with a much better multiply algorithm, that would be very valuable. A question?
Would you deal with the spikes in energy demands in a data center?
Are there spikes?
In the energy demands in data centers, and how do you deal with that at Google scale?
Yeah, well, there's this sea change that's happening from everybody. We buy CPUs to we buy for AI, even changes the data centers. So training, which goes on for weeks or months on thousands of computers, is much more flexible on spikes and stuff like that. So if you could get energy cheaper by backing off or avoiding times a day, that's pretty plausible. The inference piece, which is, there's two pieces of inference. There's a bulk inference, which is like training, it's batch job in the background, and there's user-facing stuff. The user-facing stuff will like all kinds of web interfaces, have spikes during the day depending where people are, and I don't think companies be willing to back off on that because it directly ties to their income. But a big piece of it is the training and the bulk inference, and we could have data centers designed for that. There's so much being invested. They could be located in different places, so there's opportunities there. Yeah.
So think about the power or this carbon footprint. We have been doing a lot in low power design. We have tried to reduce the power consumption of the chips and all that stuff. Have people looked at, in terms of, let's say I take a smartphone, actually, is the power is really a lot goes to the compute part, computer chips, or is actually other parts?
It's other parts.
Are we really making?
Yeah, so I think it was maybe 2/3 of the power go for the display and the wireless, and there's other devices in there, and maybe 1/3 is just compute. And currently AI is a small piece of that.
Maybe the trend going to.
And the other thing to say is, I'm given where I work, I'm data center focused. There's all kinds of edge devices, which a lot of things I said wouldn't apply. That we're battery life, and energy efficient, like Internet of Things. We looked at smartphones, but that's kind of a bigger embedded thing. So embedded things can be very different than this, but energy is going to be very important for that. Go ahead.
I was at Google 25 years ago when the AI thing was just getting started at Google, and I remember a friend of mine requisitioned 1,000 computers to run a training model, and then he confessed to me that he only needed one, but no one would take him seriously if he only did it trained on one computer. Brained it on 1,000 computers, and ran the same code 1,000, on 1,000 computers, so people would take it seriously. So I get what you're saying about the marketing and the push for reduced energy emissions, but there's also a marketing push to make it seem like you've done a big thing.
I would say from the, I am not an AI expert, but the people I hang out with, they are, the investment is so large that there's huge reward. Like my example, engineers getting paid $1 billion to go work at, if you're willing to work at Facebook, I'll give you $1 billion over 5 or 8 years. Why is that, right? Because they have all that, they've invested in the hardware, but their models suck compared to their competitors, what are they going to do, right? So I don't think people are wasting. The numbers are so big they can't waste it like they used to. Like I said, it's the biggest investment in humanities. This is bigger than the Manhattan Project that's going on. It's funded by private industry, but it's astounding what's going on. Yeah.
As you said in your earlier talk, when the kid gets out of school, it has to apply what it learned. But isn't there also this necessity of lifelong learning? So switching to our topic, shouldn't be this split between training phase and application phase somehow vanish? Or do you think?
Yeah, the only thing we've been working on AI for 70 years or something like this. This current version works, right? All those AI winners and promises that never fail. So what they're doing right now works. It seems, but it's like we're building steam engines and we don't understand thermodynamics or something, right? We don't have the theory of why it's an empirical field. Why did you do that? It works. That's where we are. And so if we had a theory underlying it, so we start off with random numbers and we train it from it feels like, if I'm around 20 years from now, we'll look back and say, oh man, if we'd only known what we were doing, it could be done tremendously more efficiently. But that just because this one style works doesn't mean all styles of AI are going to work. So there's that kind of tension there. I think I can do one more question, or not. Okay.
So Intel had this Optane system where
Right.
you don't need to refresh when you're not.
Yeah, Optane is an example of one of these, is a phase change memory, and they said, hey, this is going to be the future, and they tried to talk Micron and other people into it, and it's very hard for a new memory technology to take off. Basically, you need to find, so how did flash happen? We used to have digital cameras, right? We would get a digital camera, so they could modestly increase the rates, and then once it got good enough, we started putting it in laptops and stuff like that, so it had a growth path. So announcing a new memory technology, and if there's not a product it goes in so it can get the manufacturing up, is very hard. So that, it failed, right, Optane. It's, on paper, it looks great, but they couldn't make it, the business model didn't work, and so it was withdrawn. Okay, I think I've used up my time, so I'll turn it back over to the organizers.
It's coffee break for a half hour.